Denmark. He got his PhD in applied mathematics from the Technical University of Denmark, and he has been a full professor of mathematics at the Department of Applied Mathematics and Computer Science in DTU since 2002. So his research interests are in nonlinear dynamics and with applications to mechanics, chemistry, and biology. Today he's going to be talking about topological bifurcations in the transition from two single vortices to a pair and a single vortex in the periodic wake behind an oscillating cylinder. Welcome, Morten, and over to you.
Yeah, thank you very much for your kind introduction and for the invitation. It's great to be here. Apologies for this very long and tortuous title, but this is a very precise statement, and I hope it will be clear in a moment exactly what I will be talking about. I should say that this is part of the PhD work of my student Anne Ryelund Nielsen, and it is done in collaboration with Puneet Matharu, who did his PhD simultaneously at the University of Manchester in UK. So, I will be talking about vortices generated by the flow around bluff bodies, and to be specific, around cylinders. Everything will be in 2D, and I will show you a number of simulations. So here's a standard one, which I just caught on the internet, which is the flow around a circular cylinder at a Reynolds number of about 300, if I remember correctly. And what you see here is the vorticity field being color-coded. And what happens is that when the fluid flows around the cylinder, vorticity is generated at the boundary of the domain at the cylinder, positive below and negative above. And this vorticity is advected into the fluid in a form of a shear layer, and then the shear layer sort of breaks up and form these very well-defined vortices, known as the von Karman vortex street. So the flow here is periodic, and you see these sort of very clear structures that are generated, and they are very robust, even though these the vorticity of the individual vortices will sort of diffuse out, as you can see, as they move downstream and time is increasing. But they are very well organized structure, and this is a very robust phenomenon. This vortex shedding. It occurs at many Reynolds numbers and many body shapes, not only for cylinders. This is what we will call a 2S wake, because during a cycle, two single vortices are shed, one of positive circulation and one of negative circulation. However, if you oscillate the cylinder, so this is an example where you oscillate the cylinder transversely to the flow, then you may get other wakes, like this one, where you have what is called a P plus S wake, where P means pair and S is again single. So during a cycle, you will get two vortices shed sort of on one side of the cylinder and a single vortex on another side. So this is an experimental picture, and these vortex streets, which are more complicated than just the standard von Karman wake, they have been called exotic wakes. So this is an example of an exotic wake, and you can get things that are even more exotic if you have other body shapes. So here's a series of examples where the body is a flapping foil. You can see the foil up here. This is again experiments in a soap film, where you can get very complicated patterns like 4 pairs and 2 single being shed through a period, and other very complicated structures like this. So there's been sort of an interest to understand these exotic wakes and how they merge into one another, how they change as you change the parameters of the problem. So that's what I'm going to study. And so I will be studying the flow around a transversely oscillating cylinder. And there's sort of two ways of describing this. Of course, you can either have the cylinder fixed and having an inflow of velocity u, or you can jump up to on the cylinder and you can you can jump up onto the flow and then have the cylinder moving like a tow tank experiment, where you suppose drag it into the fluid and also oscillate it up and down. So this problem, is characterized by three-dimensional parameters. One is the Reynolds number based on the incoming flow velocity and the diameter of the cylinder and the viscosity. And I will fix this to 100 in this study here. Then there is the amplitude of the oscillations of the cylinder. These are forced oscillations. And you can then either describe the frequency of the oscillations or the wavelength of the oscillations as described here. And you will non-dimensionalize these quantities relative to the frequency or the period of the shedding frequency, the periodicity of the flow when the cylinder is stationary. So that is called the Struhal frequency or the Struhal period, and you would use that as a time unit. And you would also non-dimensionalize the amplitude of the oscillations by the diameter of the cylinder. So three parameters in all in this problem. We'll fix one, so we are back to two. And there is a very famous paper by Williamson and Roscoe where they do an experimental study of this problem. And they have also fixed the Reynolds number. Actually, it turns out that in this rather low Reynolds number range, things are not that sensitive to variations in the Reynolds number. But here you have then the two parameters. One is out of this axis here, you have the wavelength or the frequency of the oscillation of the cylinder, and up here you have the amplitude of the oscillations. And you see here various configurations with 2p and p plus s wake and 2s wakes in this diagram, and also things that are a bit difficult to see because there are regions where the flow is not periodic, so you don't have exact synchronization. And here's a picture, experimental picture from that paper. This has also been studied computationally, of course, and here are some results from a paper by Leontini and et al., which is essentially the same diagram here, but then just computationally. Forget this line, please. This is just something to do with the energy transfer I won't discuss here. But you will see here there's a region in the parameter space where we have 2s wakes, and then there's sort of a limit. And if you cross that, you will get a p plus s wake. This is sort of this curve here is a resonance tongue bound. So what's inside is called a resonance tongue or an Arnold tongue, because here you get synchronization. If you go outside, you don't get periodic solutions. But here you see we force down here exactly with the Struhal frequency, then you have resonance, and there's a general theory about forced oscillators that sort of guarantees that you have these regions where the flow synchronizes. And you see this diagram does not look quite like the experimental one, but some similarities. And here's an example of one of their computational pictures of the vorticity as well. As you saw in this one, there's this transition from 2s to p plus s in these computations, and that is exactly what I want to study. And I will concentrate on fixing the frequency at the Struhal frequency, and again Reynolds number 100, and see what's actually going on there, which in the previous diagram was just a single line here. So there's just a sort of single event changing from 2s to p plus s, and I can already say now the conclusion will be that it's much more complicated than just a single event happening, separating these two wake configurations. Anyway, so let us see here again this diagram, and for two values of the amplitude, a low one, the green one, and a higher one below this bifurcation curve, this transition curve, and one above, and you see sort of indeed after a little while things do indeed organize themselves. The flow does organize itself down here into a 2s wake, where you have one vortex of each sign being shed, but up here you have this p plus s wake, and after some initial transients. So our computations here have sort of reproduced this transition from one wake type to another. So let me get a little closer to this transition curve by Leontini et al. So let's go to the blue spot there. That's a parameter value I will study for a while here, and here we are. And what I want to discuss is how these vortex structures are changing as you change as you change the parameters. And to that end, you would sort of need to define precisely what a vortex is. And if you try to do that, the gates to hell open, because what is a vortex? And it seems that there's no sort of generally accepted precise mathematical definition of what a vortex is. There are many definitions out there. I saw a recent review paper that mentioned more than 20 different definitions of what a vortex is. Some of the more popular ones are the Q criterion and the lambda 2 criterion, much used mostly in 3D flows. But here I will use sort of the simplest thing you can reasonably do, and that is to identify a vortex by a critical point of vorticity. You say, well, here there's a vortex here, right? So there's a center of a vortex here. So I would identify a point like this as a vortex, or if you like, a vortex center. It will sort of be a natural generalization of a point vortex, where you have all vorticities concentrated in a single point by a delta function. But if you add viscosity, you will have a diffusion of vorticity, and you should have them spread out here. So I will define a vortex as a critical point of vorticity. Maybe I should wait a minute here. So there are a critical point of vorticity is one where these partial derivatives are equal to 0, and it is an extremum if the determinant of the Hessian matrix is positive. And that is what I would call a vortex, a local extremum of vorticity. But there are also other critical points of vorticity, and they have a negative determinant of the Hessian matrix, and they are saddle points. So they're sort of the physical significance of those is a little unclear, but they have to be there for topological reasons. And let me show you what happens if you identify these points here. So here I have added black dots. These are vortices, in the sense they are extrema of the extremal points of vorticity, either positive or negative. I haven't distinguished between those. And then the red points are saddle points. And what you see here, if we use, let's keep track of this orange thing here. You see there a saddle and an extremum were born here in a bifurcation. They sort of exist for a while as this structure moves downstream. And after a bit, they actually merge again. And here you are, and they disappear. So there's sort of a mirror thing going up on the top, exactly the same. And there's a symmetry in this problem here, saying that if you flip the axis of the middle axis here, you flip around that. If you add half a period and then flip the vorticity, you're back to where you started. So there's sort of a translation and reflection in time and space will give you the same velocity field as you had before. This is compatible with the system here. And what I described before was this phenomenon which is called a cusp bifurcation, where either out of nothing, an extremum and a saddle are born, or if you go the other way, they merge and disappear. And it's called a cusp bifurcation because there is a level curve of vorticity at the bifurcation point, which has this cusp shape. It's also known as a saddle center bifurcation or saddle node bifurcation. It's sort of the most elementary way you can create vortices in the vorticity field or destroy them. And we see both things happening here. And it actually, it doesn't work here. Actually, sort of the main vortices here, those that persist, they are also created the same way, but the computational method we have been using here does not allow us to resolve exactly what's going on very close to the cylinder, and that's why they just seems to pop out of nowhere. They don't. They are also created in this saddle center or cusp bifurcation. So this is what's happening, and clearly what we see here, that just describing this wake as either a P plus S or a 2S wake is too simple, because there are structural changes going on in the wake as time progresses. During the flow, there are topological bifurcations, and so just describing them in the very simple way with these symbols, P and S, is not good enough. So let me show you here just a snapshot of one of the previous simulation, where you sort of see sort of highlighting sort of the same structure when it has just been sort of advected one period downstream. So this structure was here a period ago. And like this one, and you see changes as you go along here in the topology of the vorticity field. So it seems to be necessary to have an extended classification of these wakes, and this extended classification is built up by symbols from sort of an alphabet of these sort of elementary configurations. And then you concatenate those, and the integer n describes how many times downstream this pattern occurs. So, or you add one because it may not exist for a full period, but then you still want to mention in this classification. So this this wake up here would be classified as 2p3 because there are between 2 and 3 periods where you have a 2p wake like this, or so there's a 2p, 2 pairs of vortices, and then the 2 of the vortices disappear and you're back to 2 single vortices, and this sort of goes on in the rest of the wake. And of course, this is a numerical study, so what happens very far downstream we haven't checked, so this is sort of a numerical in infinity. It's well known that there are reconfigurations of the wake if you go hundreds of diameters downstream, but I'm not thinking about this, so you should just think of this infinite symbol as being a very large number in practice. So this is all very nice. This flow is complicated a bit by the fact that it is bistable. So again, I'm still having the same value of the amplitude of oscillations here, and this was a solution I showed you before. But at the same parameter value, there's also another stable solution, which is this one, and which has clearly a different topology. So this is something which is resembling a 2s wake, and this is a p plus s wake, at least after a while. But they coexist at the same parameter value. And why is that? Well, and I should notice then that this one fulfills the symmetry I described before, but this one doesn't. I mean, you can't reflect this pattern here in any way and get back to itself because of these extra vortex coming here. So there's a symmetry breaking going on here. And this has been studied in detail by one of my co-authors as a part of his PhD work. And it turns out that there is a symmetry breaking pitchfork bifurcation from the symmetric branch. So there's a branch of symmetric solutions, the one I've showed you before. I'll measure the deviation from symmetry by the norm of this quantity here. So if the symmetry is fulfilled, then this is identically 0. This norm, if there is a lack of symmetry, then this is different from 0. So there is a branch for low values of the forcing amplitude. There is a family of symmetric solutions as the one we have seen before, but then at some value A2, which is 1.093 for Reynolds number 100, this branch loses stability. It still exists for a higher value of A, but it has lost stability. But then out of this point, another asymmetric branch of solutions characterized by non-zero epsilon is created. And these new solutions are, when you're close to this point here, they are unstable. And so they coexist with the stable symmetric solution. But this branch turns around in a fold bifurcation and gains stability. So you will have a bifurcation diagram like this. And there is a range of bistability between the fold bifurcation and the symmetry breaking bifurcation. It's a very narrow region. You see these two numbers are almost identical, but the case I showed you before is indeed in this region, very close to A2, in fact. So that's why you can see either this solution or that solution, depending on the initial conditions. On top of these topological bifurcation I've shown you, there are also this dynamical bifurcation occurring. And at this stage, I would like to spend just 2 minutes discussing the different types of bifurcations in fluid mechanics. I think that's a point that's been often overlooked because there are essentially two dynamical systems at work here. One is the Navier-Stokes equations, which you can think of as a dynamical systems in an infinite dimensional space. of velocity fields. And you could, for instance, say that in fluid mechanics language, a steady flow. In dynamical systems language, it could be called a fixed point. So that's a certain velocity field, which doesn't vary with time. A periodic flow would be a limit cycle, and so on. So you can have dynamical bifurcations. They are bifurcations that occur in this dynamical system if you vary a parameter, for instance, the Reynolds number or something like that. And one could be a Hopf bifurcation, where a fixed point loses stability and a limit cycle occurs. And that is the bifurcation that is responsible for creating the standard von Karman wake for a steady cylinder at a Reynolds number of 48 or something like that. That is a supercritical Hopf bifurcation in the Navier-Stokes equations that gives rise to this periodic flow. But there's also another type of bifurcation. If we look here, we look at vorticity, and the level curves of vorticity, including the extremal points on the saddle points, they are solutions to this dynamical system, which is a two-dimensional dynamical system. So this lives somewhere different. And a topological bifurcation is a bifurcation in this dynamical system. For instance, a cost bifurcation where vortices are created or destroyed. And they can occur under variation of parameters, or as we're doing here, really considering time as a parameter. So you can write this dynamical system in the plane up as a dynamical system depending on time as a parameter, because time does not, for any fixed time, you may consider the topology of the vorticity field by solving these equations. So it does not appear explicitly, it appears only as a parameter in this system. So these are different types of bifurcations, and I think it's difficult to understand that they are sort of independent because they happen in, well, the mathematician would say, in different spaces. And we have both here. So these cost bifurcations are topological bifurcations. The symmetry breaking bifurcation is a dynamical bifurcation in infinite dimensional space. So to go back to the point we want to address, really, what's going on as we increase across this this symmetry breaking bifurcation? What implications does that have for the topology of the wake? And it's described in this bifurcation diagram, and I'll walk you through it. So what you see here is the parameter A up here, and down here we have downstream distance from the cylinder in dimensionless variables x here. So let's start with a very low value of A, less than this point here. Then you have only single vortices being shed, two single vortices being shed through every period. So you have the classical 2s wake with no variations in the topology as you go along. But then you see here there's a value A0, 0.85 or something like that. So if you cross that and go just a bit about that, you will see that there will be if you are close to the cylinder, you have a 2s wake. Then you have a cost bifurcation, creating new vortices, and they go downstream, and then they disappear a little later, and then you are back to the 2s wake. So you will, in this region here, the gray region, you have 4 vortices, so in a 2p configuration. But then before that and after that, you are back to only single vortices. And as you increase the value of A, the number n gets smaller and p gets larger as you move up here.
Morten, sorry to interrupt. Maybe you could finish in a couple of minutes.
I will finish in a couple of minutes.
Okay, thank you.
Yeah, I'm almost done. If you go to so that happens until you. I can continue on this branch. So I'm living here in the symmetric branch, and I'm on the symmetric branch. If I increase A until I reach A2, this dynamical bifurcation point. If I increase above A2, then I jump to this asymmetric branch, and then the asymmetric branch allows these asymmetric P plus S configurations. So there's sort of a discontinuity in the pattern as I cross A2, because I go away from that branch and into this one. And then I can get wakes like this, where you have P plus S in the beginning, and then you have a period of 2P, and then you go back to P plus S. And as you increase A, the region with 2P things disappear, and you will finally, if you're above this level here, you will go back to sort of a full P plus S wake. So if you go backwards, it's a bit different. I will skip the details here. So just varying a bit the forcing period, you will see these 4 bifurcation events. So going from so this was my A0, or you can see it here, a detail here. Only one type of vortices below A0, a combination between A0 and A3, and then only a P plus S if you go over A3. So there are actually sort of 4 essential bifurcation events here, where you change from one type to another, and not just a single curve as normally assumed. So that is actually what I wanted to say. Actually, the transition takes place over a large interval of forcing periods. So you see there's a rather large interval of A values where this occurs. And you need to extend the classification scheme by Williamson and Roscoe to describe these stages, because they're intermediate topologies occurring in the wake. And there are these key amplitude values where you have these where you change from one type to another, where these intermediate things they disappear. The key here at this point is that this symmetry breaking bifurcation is needed to have these P plus S wakes, because otherwise you are in trouble with having non-symmetric. And I think these sort of intermediate local patterns which occur, if you look closely enough, they may be related to the problem of the missing 2P wake. If you do numerical simulations, you don't see the 2P wake. It doesn't occur. The full 2P wake, as you see in experiments, does not appear in simulations. So maybe this has something to do with they actually do sort of partially exist, and that could sort of shed some light on this problem here. Okay, so you can find details about all of this in this paper here, and thank you very much for your attention.
Okay, thank you very much for your very nice presentation. So if anybody has questions, please go ahead. Maybe I can just start by asking a quick question. So you mentioned the 2 different types of bifurcations, right? And also like the X dot is the derivative of the vorticity, etc., the dynamical system with the vorticity in it. So, but if this is created.
Oh, I'm losing you.
Yeah, I think I also lost Vikas.
Yeah. Okay.
So meanwhile, Vikas gets connected. If anyone from the audience has question, they can feel free to ask to Morten. Okay, he's back. So because we lost you.
Yes, sorry.
We lost you. Yeah.
Yes, so I was just asking, so in these equations, where does viscosity appear? I mean, in the vorticity equation here, in the second point.
Oh, so viscosity appears because you obtain this vorticity field from a Navier-Stokes simulation. So
oh, I see. Okay.
Yeah. So you have a family of solutions parameterized by time, and that's where vorticity comes in. But this is a Hamiltonian system, really, of course, for the level curves. Yeah.
I see. Okay.
Yeah.
Thank you.
Yeah.
And also maybe just another quick question. So you are so how are these can we see the same bifurcations irrespective of like the shape of the oscillator? Because experimentally you also have these the foils which oscillate or cylinders, etc. So do you see the same type of bifurcations in all of these wakes? I mean, when you're doing it computationally?
Well, yes. I mean, I think so there you see this bifurcation, right? If you put it here two vortices come together and merge.
So
yeah, I mean, a vortex and a saddle, excuse me, and disappear. Yeah.
So yeah, I mean, if you change the cylinder to a foil, do you still see the same exact thing happening?
Yeah. Yeah. So I mean, the details vary, of course, depending on the shape of the body. But I mean, it's still the same ingredients because only so much can happen. And this is, well, I mean, this is the codimension one bifurcation that can occur in level sets. You would see that bifurcation in all kinds of two-dimensional flows where there are sort of vortices, where vorticity is relevant. Yeah, so it's sort of the same toolbox, a very small one, no matter what. Yeah.
Okay, thank you.
Yeah.
Okay. Anybody else has any question? Okay, so thank you again, Morten, and let's move on to the next speaker.
I suppose I have to. Here we go.
Okay, thank you. So our next speaker is Dr. Sangashri Mukhopadhyay. Sangashri, are you here?